Okay, welcome back. Announcement concerning the seating rule. You go ahead and sit wherever you feel comfortable. You don't have to worry about the railing. I want to talk about total internal reflection. If you have two substances for which the index of refraction N is fairly close together, you can, and actually they don't have to be close together, you can experience something or observe something called total internal reflection. And what I have here in this diagram, I'll explain it to you. This is here in the center. Let me get this cursor over here. Here we go. Okay, here in the center, this circular part of the diagram is meant to symbolize a cross-sectional view of a fiber optic cable without the insulating, without the plastic that coats it. So the guts of a fiber optic cable is a core indicated by light green here, surrounded by another layer of glass that is slightly different index of refraction. And so this white area is a different flavor of glass, a different kind of glass. And here are the specs for the core of the fiber optic cable in this example. And this is the example from the textbook, by the way. The index of refraction is 1.667. That's for a specific kind of glass. For a different kind of glass, the specific, not specific heat, the index of refraction is 1.523. Now over here is a cross-sectional view, this part where it has straight lines. This is a cross-sectional view cutting along the length of the cable. So you can see the green inner area, and then this outer layer is called the cladding, C-L-A-D-D-I-N-G. That's the different kind of glass. That's N2. Now I didn't put N2 in the white area, but you can pencil it in your diagram if you like. Now what I did in here was make an example of a red light ray that goes from somewhere inside the core and interacts with this boundary between the core and the cladding. At that boundary, depending on the angle, it will refract. Some of it will reflect. All right, at this angle, you'll get a little bit of reflection and a little bit of refraction. Okay? And the angle of incidence, I've got over here the angle theta 1, which is this, I don't have it labeled in the diagram, but this one right here. Between the normal and the incoming ray, okay, so that's theta 1. And then theta 2 is up here. Well, here's a blow up of that point. Theta 2 is this angle between the normal to the surface and the outgoing ray. Okay, so this upper part here is the outgoing ray. And the same thing up here. That's a little bit better of a diagram down here. Now it goes almost straight. And there's a reason for that. But go ahead and make yourself a note. This angle here, theta 2, it just comes out of Snell's law. N1 sine theta 1 equals N2 sine theta 2. Okay, this is theta 2. And if you do the inverse sine, you can figure, the quotient of N1 and N2 and the sine of theta 1, you can figure out what theta 2 is. So it comes in at 30 degrees angle of incidence, and because it refracts, it bends just a little bit. It bends away from the normal. All right, so it comes in at 30, and it goes out at 33. So that's pretty close. And matter of fact, it's kind of hard to see. I don't know if you guys can see it. It looks pretty straight. Right now, when we change the angle, you'll see that the angle is more noticeably, or the interaction leads to a bigger bend. But right here, it's almost straight. Now, before we go to the next, have your clickers ready. We have a clicker question. Matter of fact, let me get the clicker set up. Okay, we're going to do a clicker question relative to this. And then we're going to build the after the clicker question, we're going to build the rest of the table. Wrong cursor. We're going to build the rest of this table. This is the first row in this table. Okay, 30 and 33.180. Now, a question. All right, here's your question. Read carefully. That's just a copy of the diagram from the previous slide. Students, by the way, hit the send. This is short answer, so type in your letter and then hit the send key. Oh, I just blooped it. All right, sorry about that. I was trying. Okay, do your answer again. Hit the refresh key and do your answer again. There's no letter E, so if you just typed in the letter E, yeah, okay, good. Okay, 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now, I'm going to show you the results here. Okay, there's our distribution. So clearly D is the most popular, and the majority of students voted for D. However, D is also correct. So, now I wasn't trying to psych your mind or anything like that, but that's why whenever I give a short answer question, that means that there's probably at least two correct answers. And B and D are both correct. They're both different ways of saying the same thing. And here it is. The index of refraction encodes the speed of light of whatever medium that you're in relative to C, the speed of light in a vacuum, where there's no, by definition, Natalie, there's no, there's no material in a vacuum. Okay, so speed of light in a vacuum on top, speed of light in a material medium on the bottom. That quotient is known as the index of refraction. All right, let's do another one. Okay, second line down on the table, 45s. 50.711, and here it is. Here's the diagram of it. It'll probably be difficult to graph that in, but you can graph it in and then let the numbers do the talking. So this incoming should come in at 45, and I measured it very carefully. And then this one is 50.71, a little bit more than 40. So you know what you could do is draw a 45-degree line all the way through that point, but on the way out of the point, make it a dotted 45-degree line, and then make your ray just a few degrees dipped below that 45-degree line. So draw that 45 in right up in here, the first quadrant, and then dip your ray a little bit below that. And so if you look at this, okay, 30 degrees, and this one, the outgoing angle is 3 degrees bigger than that. 45 degrees, the outgoing angle is 5.711 degrees bigger than that. All right, let's try another one. 60 degrees. So this angle down here, here's your angle of incidence. This one probably you can do pretty well. 60 degree, that's the same size as a equilateral triangle, equilateral, equiangular. So you might be able to visually estimate that down here. And then, whoa, definitely starting to see the bend here because it dips all the way down to 71 degrees in angle theta 2 here where my cursor is, 71.425. Okay, so you go up another 15 degrees, angle of incidence. See, there's 15 between all three of these. Okay, and then 15 degrees here, you get another 20 degrees, another 11 degrees away from your angle of incidence. So it goes in at 60, but it doesn't come out at 60. It refracts. Okay, and it's nonlinear. Theoretically, it's nonlinear. And we'll see the nonlinearity in just a second. Let's do 65. Whoa. So cut this one in at even less of an angle. So this theta 1 down here is 65 now. And go ahead and jot down the table, and Asia, we're just going to let the numbers do the talking. All right? And then the outgoing angle is even bigger, 82.747. And eventually, hopefully, you'll be able to see that this outgoing ray is going to, if I if I increase my angle of incidence, eventually this output angle here is going to be 90 degrees. All right? And when that happens, it's right on the boundary. It's not going in or out of the boundary. That's a problem. All right? Now, here's what it looks like as a graph. You can graph this up. From 0 to 90 vertical, from 0 to 90 horizontal. Okay, this down here is the angle of incidence on the horizontal scale. And so just makes, 6 lines horizontally, 6 lines vertically. Each line being 15. And and I started this graph down here at 5 degrees. And here's 15 degrees where we started. No, we started up here at 30, and here's 33, a little bit higher. So nothing is on this 45 degree line. It continues to go away from the 45 degree line. So that's from northeast corner down to southwest corner. That 45 degree line on the graph paper is not where the angle of refraction ends up. It's above that line. And eventually it kind of takes a left turn here and shoots for the moon up here. So give that a good curve there. You can see this is not a linear. It looks linear down here. And for small angles, it is approximately linear. But there is curve to it at every part, even though it's a fairly quiet curve, very gradual. But it gets tighter and tighter. And up here, it definitely starts to shoot. Okay. Now right here, this last angle, where you're almost at 90 degrees here, it looks like you're at, 60-something degrees. So maybe 65 or so, something like that. When you get to that angle, you have the outgoing ray folded all the way down into the surface. So it's not going in, it's not going down. It's just along the surface. And that's what we call the critical incoming angle. Okay? And so that's our big question mark. What's happening up here? And what happens up there is total internal reflection. And here's 66. I went 1 degree bigger on my incoming angle. And so that you could see the red outgoing ray, I made it really, really thick. This is like 15 pixels thick. So you can see it because it's right on top of this blue boundary. And if I made it the same thickness as this incoming, you wouldn't see it. Right? Now this is 89 degrees, 0.282. It's almost 90. All right, so my critical angle is probably somewhere between 66 and 67 for this pairing of the two types of glass, crown glass and flint glass. That's the two different kinds of glass in the table. Kimberly.
So the N2 degrees that we're getting, that's in respect to the normal?
That's correct. So this, you go back to this. This angle right here, this is the incoming angle. That's theta I, angle of incidence. And that's 66. 66 from the normal out to the incoming ray. And then the same thing here. Now this is 89 from the normal all the way down here to this outgoing really thick ray. Okay, so that's almost 90. All right. Now how do you find out the critical angle? Well, what you do is you take Snell's law and you put 90 degrees into the sign. Okay? So it's N1 sine theta 1 equals N2 sine theta 2. All right, make theta 2 your outgoing angle, make that 90. And the sine of 90 degrees is just 1. All right? So that's kind of cinchy. And so my theta, and now I've got the C subscript here to indicate this is the angle at which I'm completely dipped down to 90 degree outgoing. In fact, that's the angle at which refraction stops. But reflection is still in operation. And at that angle, you still have reflection. In fact, you have all reflection. All of the light reflects. Total internal reflection. And that happens in the core. The light stays in the core. It cannot escape if it's got this angle or more. So let's figure this out. Sine theta of C is equal to the quotient N2 over N1. All right, that's pretty cinchy. And we got those two we have those two indices on the previous table. All right. So you can figure out the quotient. And then just do the inverse sine, and you can get theta C by itself. All right. So Diamante, this is how we're going to do, welcome back. This is how we're going to do the critical angle beyond which no refraction hits or occurs, beyond which you only get internal reflection. So the only interaction at the boundary for angle of incidence here and bigger is reflection, only reflection. And actually, you know how you see this in a swimming pool? If this will take place in for any boundary really, between so air and water in a swimming pool. If you go down deep enough and you look along the surface, if you know how to open up your eyes underneath water, or you're wearing a scuba mask and you look along the surface, eventually at a certain angle you can see people above, outside the pool. So if your friend is standing by the side of the pool and you're over there, how come you didn't come to office hours? You were in there, weren't you? No? Okay. I thought I saw somebody in there. Okay. So you're in the pool, you look at it, your friend's standing by the side of the pool, all right? But if you back up a little bit and change the angle to get to look at that person, all of a sudden, the surface of the pool starts to look like a mirror. Looks silvery and wavy, if there's any kind of waves in the pool. You try it next time you're in a pool, you'll see. It's kind of cool. So there's the angle. Now, I want to do some dot-cam examples with you. And then we'll talk about exam 3. So let me pause the YouTube for a second, for a few seconds. Okay, so we just worked out some examples on the document camera. And now we're going to dismiss a few minutes early today. But before we do, I want to give you some final comments. And I'll entertain questions from the floor about exam 3. Now, we'll start with my comments. Comment number 1. Chapter 27 will not be on exam 3. We'll do that next week. We just don't have time for it. Now, you did a little bit of reading in it already, so that's good. 2. Students have been asking me about the different sections. I don't really have the list of sections off the top of my head, but if you look, as I've said many times, if you look at your lecture notes, you can kind of work out what the sections are. I mean, I know what the chapters are, but if you look at your lecture notes, then look in the book, you should be able to kind of figure out what sections. And so you can post, if you figure out what you think the sections are, post them in that discussion thread. It's already started. And I might, if I have time, but I have to write your guys' exam tonight. So I'm not going to ask you to do anything more than what we do tomorrow. Before the lecture tomorrow, we'll dismiss in a few minutes here. Tomorrow, for the beginning of lecture, we'll do the human eye from chapter 26. And I probably will not do any lens calculations with you on the test. But we've done a bunch of mirror calculations. So don't be surprised if you see some mirror calculations and some mirror concepts. I might give you a diagram of a mirror system. Okay. Helena. And then, ask you some concept questions to follow it, or some concept questions to lead into the calculation. All right? Come on down. It's all right. It's fine. Or, oh, okay. Oh, all right. I thought you were going to refill your coffee. Okay. In office hours today, we were talking, about the exam. And you guys that were in office hours, I'll ask you for questions here, and I'll ask you guys the questions in a second. The pattern on exams for me is, if you think about what you see in lecture and homework, you'll be able to figure out my obsessions, the things that I think about a lot. In addition to the Green Bay Packers, one of my obsessions. The other things, I'll tell you what one of my biggest obsessions is diffraction, but it won't be on this test. It'll be on the final though. And we'll tackle diffraction on Monday. And you could bet your bottom dollar, the last dollar in your wallet, that you'll see diffraction out the wazoo on the final. Well, maybe not out the wazoo, but semi out the wazoo on the final. But if you look back at your notes prior to exam 1 and your homeworks and think, all right, now how does that compare to what Dr. Brickner actually wrote on exam 1? And then do the same thing. The stuff after exam 1 and leading up to exam 2, homework and lecture, we talked an awful lot about mass spectrometer, velocity selector, and those were both on the exam. We talked an awful lot about, unfortunately, the right-hand rule, and that was, we had to. And guess what? A student was asking me, hey, Dr. B, is this the only right-hand rule that's going to be on the exam? And I told the student, it's the only new one. The new one, the most recent right-hand rule is the one involving the electromagnetic field orientation. The electric field, my upright fingers curl down to where the magnetic field is, and then the thumb is the direction of the propagation of the electromagnetic waves. So that's the only new one. So as I was mentioning, you should be able to figure out or get a good idea of the general idea of what I'm going to ask you about calculation-wise and concept-wise for the tougher questions. Now, I'm going to trot you through the basics. Okay? So like, what is lambda? You'll have a bunch of constants on the cover page. You'll have a bunch of diagrams. And I'm really getting, one of my obsessions is diagrams. I never put as many, 3 pages of diagrams. I've never done that before on a test. But with you guys, I just feel motivated to do that. So, all the equations that, we've talked about a bunch of different equations and stuff. All the ones that you need, Megan, are going to be on the matching. All right? Just like last time and just like exam 1. And there might be a few extras in there that you don't have to match, but they're going to be true equations. So 25 questions, 50 points. And if you do better on this one than exam 1 or better than exam 2, we'll keep this one and drop the one that's lower. So remember, that's after tomorrow, we'll be able to do that. All right? Because we'll have 3 exams on the book. Bring your Scantron, your calculator, and wait a minute now. I haven't opened up the floor for questions, and I know you're going to have questions. Let's do the questions now before everybody dismisses. But Mr. Liesel, let me before we get to you, I'll get to you in a second. You guys that were in office hours today, is there anything else that you think I should mention? Anna, where are you, Anna? Elizabeth and Holly, anything else? All right. Ryan, what do you think? Anything I should? Okay. I think there were a few other. Let's go first with Mr. Liesel. Okay, we'll open it up. Go ahead. Have you what? Oh, for the written homework assignment, I decided not to do that either. So you're going to have, I'll put it up. It's going to be cinchy. It's problem 38. And I'll just explain it to you. You can see the PDF as soon as you get out of class. Well, 5 minutes after you leave. You're going to do problem 38, and you're going to make a nice sketch. That's the difference. You're going to make the calculation. It shouldn't be too bodacious. And I want you to make a diagram that is accurate enough that you can say, see, Dr. B, I'm letting my numbers do the talking, but my diagram's pretty good too. Just like I did yesterday, okay? Using the straight edge and graph paper. So the variation on this homework is that you're going to be allowed to hand it in on graph paper. So if you don't have any graph paper, find a friend that has some and get 1 or 2 pages. But you know the other thing is, if you don't have graph paper and you have the handout, you can, if you use a ruler, you should be able to work out. But you're going to have to, the thing about that problem, some of the numbers are kind of big. I think one of them's 52 or 39 or something like that. So you won't have 39 inches, you won't have 39 centimeters, but yet, you might multiply by 2 and count 78 millimeters. That you might be able to do. So you can do it on the regular handout, but with a straight edge, a ruler. Do tomorrow. It's a simple calculation and make a good diagram. I just hope it doesn't take a huge amount of time. It shouldn't. I mean, maybe half an hour, but make it good. Yeah. Chapter 23 we actually talked about last Wednesday. So it was in our lecture. We talked of just a few concepts at the end of chapter 23 with the RLC circuits and stuff, resonance. Conceptual questions? Yeah. Well, everything that we talked about from last Wednesday up until tomorrow morning, or tomorrow 3 to 3:45, is fair game. Another question. Yes. You should look over what? Yeah, if you haven't finished reading chapter 26 about the human eye, go ahead and do that. We'll talk about, and I'll probably have some clicker questions for you tomorrow about the human eye. And because that's the case, you might find similar questions on the exam. I can't be sure because I haven't written the exam, but if you come to class with your eye clicker tomorrow, you're golden. Another question. Yes.
So to be clear, lenses isn't on exam 3, but it's on the final.
Lenses?
Yeah,
Lenses is chapter 26. And the human eye, we're going to talk about it in terms of lenses tomorrow. No lens calculation, yeah. Yeah, so we're not going to be doing diagrams, but the human eye is a lensing system. So when I talk about that, expect to see some lensing questions on the exam tomorrow. They might not be so you're not going to see lensing human eyeball equations on the test and calculations, but concepts, yes. All right? Yes.
Do we need to know the different wavelength frequencies of the electromagnetic spectrum?
Okay, see, we should have. The question was, do we need to know the different frequencies and wavelengths of the electromagnetic? You mean X-rays versus ultraviolet versus? No, and you know what I might do is give you a diagram, a graphic, not the one in the book because I don't like that one, but maybe an equivalent one that's compact. But you know what we were talking about in office hours, I always have to look stuff up of that kind, except for this. I always remember Roy G. Biv visible band, 400 to 700 nanometers. Other than that, I just go look it up. All right, so if you remember 400 to 700 nanometers, you're golden. And then there'll probably be some kind of a diagram in the. So the cover page won't be just diagrams to calculate with, but something like that to help you think. Another question? Yes. More homework? Okay, you guys in favor of that? More homework? Problems that I like? Yeah. Well, 38, I announced that one in class. It's not on the list yet, but I'll put it in there. I might put a few more in. I'll look through chapter 26, see if there's a few in there. Okay. I'll try to do that tonight, so you have something extra to study with. And hey, you guys, that student knows the way I think. Because the problems that I like, and usually in some manner or form, end up on exams. Why? Because I like them. And I like them because they are important. Ding, ding.
All right, you're dismissed. I'll put the homework PDF up in 2 seconds.